All right, get ready for this. We're about to explore one of the most unexpected, just beautiful connections in all of mathematics. And believe it or not, it all starts with something as simple as dropping a needle on the floor.
So if I ask you, where does pi come from? What's the first thing that pops into your head? It's circles, right? Yeah, pretty much all of us learned that it's the circumference of a circle divided by its diameter. Classic. But what if I told you that you can find pi without any circles at all? What if you could calculate it just by randomly tossing needles onto a lined piece of paper? I know, it sounds totally made up, but that is exactly what we're going to dig into. And this all leads us to a famous problem from way back in the 18th century. It's called Buffon's needle experiment. It's a really famous problem in a field called geometric probability. And the whole idea is just beautifully simple. Take a needle, drop it on some lines, and see what happens. The real magic here is that this isn't some abstract thought experiment. It's a physical, drop and count kind of thing. You don't need fancy equipment or complex math. All you need is a needle, some paper, and, well, a whole lot of patience to find one of the most important numbers in the entire universe. So, how does it actually work? Well, it's pretty straightforward. First, you get your setup ready. And here's the key part. The space between your parallel lines has to be exactly the same as the length of your needle. Then, the fun part, you just start dropping it, over and over, randomly. As you go, you keep two counts. The total number of drops, we'll call that N, and the number of times a needle actually crosses one of the lines, we'll call that C. And then you plug those two simple numbers into a special formula, and out comes your estimate for pi. Okay, so this is what it looks like before we begin. Just a clean slate, you know? We've got our lines ready to go, our drop count and our crossing count are both at 0, and our estimate for pi is, well, it's nothing yet. Now, after a handful of drops, maybe 85 or so, you'll get a result. Here, it's about 3.03. I mean, it's kind of in the right neighborhood, but it's not super close, is it? And that makes sense. With a small number of tries, random chance is going to give you some pretty wonky results. But here is where the magic happens. Look what happens when you keep going. After 30,000 drops, look at that number, 3.14103. That is unbelievably close to the actual value of pi. This isn't just a lucky guess. This shows us that a predictable, orderly pattern can actually emerge from complete randomness as long as you do it enough times. And this, of course, brings us to the biggest question of all. How on earth does this work? How can something so random, just tossing a needle, pinpoint a number that defines the perfection of a circle? The whole secret is buried in probability. For any single needle drop, we just need to figure out the odds that it's going to cross a line. Let's call that a hit. And those odds really depend on just two things, the needle's position and the angle it lands at. So, it all boils down to this one simple rule. A needle crosses a line, it's a hit, only if its distance to the nearest line, let's call that D, is less than the vertical height of the needle. So if the needle is too far away, it's a miss. If it's close enough, it's a hit. It's really as simple as that. And this graph, this is fantastic. It shows us the whole picture. Think of this as a map of every single possible outcome. The bottom axis represents the angle the needle lands at, from flat to upright, and the side axis is its distance from a line. That whole rectangle contains every single possibility. Now, see that red shaded area? That's the sweet spot. That area represents every single combination of angle and distance where the needle crosses a line, where that hit condition we just talked about is true. If your needle's random drop lands it in the red zone, it's a cross. If it lands in the white area, it's a miss. So, figuring out the probability becomes a simple geometry problem. All we have to do is figure out the ratio of the red area to the total area of the rectangle. You know, what fraction of all the possible ways a needle can land results in a hit? And when you do the math, which, okay, it does involve a little bit of calculus to find the area under that curve, the answer you get is just mind-blowing. It's exactly 2 divided by pi. The probability of a random needle hitting a line is 2 over pi. It's just built right into the fabric of the universe. It's incredible. And this right here connects all that math back to our actual experiment. The fraction of needles that we counted crossing a line, remember, C divided by N, that fraction should get closer and closer to that theoretical number, 2 over pi, the more and more needles we drop. And now, with just a tiny bit of algebra, we get our magic formula.
If c over n is roughly 2 over pi, we can just flip both sides of the equation and multiply by 2 to get pi all by itself. And there you have it. Pi is approximately 2 times the total number of drops divided by the number of crossings.
So let's really put it to the test with a massive simulation. After more than 329,000 drops, we end up with about 210,000 crossings. We plug those huge numbers into our formula, and we get an approximation of about 3.136. It's not perfect, but for something based on random chance, it's amazingly close. It proves that this wild idea actually works.
So why is this so important? I mean, this is way more than just a neat party trick. This experiment shows us that pi isn't just about circles. It's this fundamental constant that's literally woven into the mathematics of pure chance. It's an incredible example of how deep, predictable order can just emerge from what looks like total chaos. It's like finding a hidden bridge between the world of geometry and the world of probability.
And that really just leaves us with one final awe-inspiring thought. If a number as profound as pi can be found just by scattering needles on the floor, it really makes you wonder, doesn't it? What other deep truths of the universe are hiding all around us, just waiting in the most unexpected places for us to find them?